Okay, now we move to the next presenter, Mr. Dr. Roni Irnawan, which he already prepared the presentation about how to the development of learning and lab work module for the course renewable energy course or any other course related with electrical engineering, which can utilize the Typhon Hill. Please, Dr. Roni, the time is yours.
Yeah, thank you very much, Dr. Satya. Pakai ini. Thank you, Dr. Satya, for the brief introduction. So yeah, I will try to continue what Marcus has shared with us. Yeah. Leave computer admin. Leave computer admin. Yeah. Now I guess it's better. Good. So I will continue what Marcus has said, and it will be regarding the Typhoon implementation that we had in our department. Actually, the Typhoon is over there, the one that we have just in the corner. So we have a Typhoon 604, and we purchased it in 2020, just before COVID. So we purchased it, and then it was COVID, and everyone works from home. So we haven't got any chance in 2020 to use it, to optimize it. But yeah, let me just share my screen. Okay, and then yeah, it will be regarding the teaching and lab work using Typhon Hill. So it might be, I mean, some of the part that I will explain is not yet becoming the part of the curriculum that we have in university, but we will plan to have it maybe in the next year to include it in the curriculum. So what I will present is the preparation to going there. So preparing the teaching and lab work modules using Typhon Hill to support the education in here. So the agenda will be I will present regarding myself and my passion in simulation, power system simulation, and also Typhon Hill, especially the virtual hill, because the most of the part, the hill part, has been explained by Marcus, and actually I will take small part to explain regarding the virtual hill. I believe Marcus has also give you a demo on how to use virtual hill, because he doesn't have the hill devices with him right now, so he ran in virtual hill mode. But we will use this one, especially the virtual hill feature, to I mean, we will use that for the education in here in UGM. And I will play around with the two words in here, that's the simulate to understand, and after we understand, we take a different level, like the advanced level, and try to have a simulation building from scratch. And I will show that some example of the project that we have, and also the modules that we already developed. And I will close with the conclusions. So regarding myself, I was working in ABB before as a design engineer. So in Sweden, in ABB HVDC. So it's the power electronic mostly, and I was responsible for doing or for developing the HVDC model, and it was the real-time, not real-time, but it's a RMS, or the electromechanical transient for that kind of purposes. So I developed a model, and if you download the brochure from ABB, I guess you still can see my picture over there. So I developed the model and becoming a model as well for ABB HVDC. And yeah, familiarize myself with some commercial softwares for power system analysis like PSCAD, PSSC, Power Factory, and Automac. All of those are offline, so it's not it's a they are different beasts as compared to Typhoon, because Typhoon is a real time. We also use Opal RT or RTDS for the real time, but I'm not involved in that part. And then I took my PhD after that in 2015 and 2018 as a fellow in energy technology in Aalborg University, Denmark. Actually, that was the first time I know about Typhon HIL, because we had a like something like this, a workshop in Aalborg, and representative from Typhon HIL came and started to explain that this is a new real-time simulator that yeah, quite good, right? I mean, it's coming, and then yeah, we also purchased, I guess, in Aalborg. We already have some HIL devices over there. And I was part of Cobra Cable research project, so I need to mention this one because yeah, previously I when I do some presentation, I need to have the same thing in the right hand side corner over here, that it's sponsored by European Union. So the Cobra Cable project was also sponsored with that. So it's kind of, yeah, okay. Reminding myself that it was the same European Union project as MESfIA. And at that time, I also spent 3 months staying abroad in U of M, or University of Manitoba in Canada. And I was under supervision of Dr. Anigole. So to those who know him, he was the one who developed PSCAD. I guess it was his PhD thesis, develop a model of synchronous generator in Fortran, and that was the starting point of PSCAD that now is used in around the world, right? And also there is a company over there, it's called RTDS, that is the pioneer for the real-time digital simulator. And yeah, it names real-time digital simulator, and they have this abbreviation, and IEEE cannot use the same abbreviation for real-time, so they use different abbreviation like DRTS right now, digital real-time simulator, because RTDS has been trademarked for this guy. So it was a mecca for simulation, EMT simulation. So having a chance to meet Dr. Anigole is quite good, and we exchanged a lot regarding the vision of simulation. And I graduated in 2019. I have my thesis recognized in Springer thesis. This is the one, you can buy it in Springer as well. And I got the C-grade thesis award in 2020. And the thing that I'm most proud of from my PhD thesis was this one. I could work with different language in here. There is a Python, C, C++, and Fortran, because each program they have their own requirement. Like PSCAD, they use Fortran in behind, especially the EMDDC library that they use, for developing control system, or yeah, I mean the model control for that. Can develop the C++ for that. And when I did my PhD, I was using Python to develop the control for HVDC. And yeah, it was, this is not good enough, because well, I mean, as a student, we are allowed to be failed, right? So this is not what is called, it's not optimized, because I can it should be coded in Fortran, either Fortran or C++. But as a student, yeah, we try different things, and this works for me, and yeah, so I got my PhD because of that. So yeah, Python, Fortran, C++, and then I came back here to join a university in 2020, and at that time I was also teaching power system related courses in different level, in a bachelor or in a master as well, and numerical methods I also teach those as well. And regarding research, the topic that I have right now, we have HVDC research topic, and also the microgrid side. And also, yeah, I'm started using Typhon Hill since the beginning in here. So we got Typhon Hill from MESfIA, and I would like to thank you, because we at that time we had there are several alternatives, but we choose to use Typhon Hill, and one of the reason is this one, because yeah, we can use the virtual hill. So what is virtual hill? As Marcus has explained, this is actually, well, this is not the one that we have. We have 604, meaning that we have more input output for the device. So we have the device, and we have also the software that can be used to run the device. And actually, virtual hill is when we only use the software without using the real-time device. So the tool chain or the process will be the same. Either you are using the device, the hill device, or not. You still, I mean, you still develop the schematic diagram, and then you develop the user interface, the SCADA user interface, and run the simulation over there. The only difference is that it's not real time, right? It is offline simulation. So as what Marcus shown in the previous presentation, and I will try to also show some of the simulation as well. So the only difference when we are using the hill or not using the hill is the real time. We lose the real time, but it doesn't mean that we cannot use it. I mean, as compared to the other vendor, I guess only Typhon that offers this kind of opportunity, so we can use the offline simulation for the project. And when it is ready with the same stuff or with the same model, we can just connect the hill device and run it. So there is no need to change that one. I mean, moving from the Typhon Hill is using the EMT simulation, like the electromagnetic transient simulator. So it is based on EMT. And when we are doing, like, for example, in PSCAD, we are also doing the EMT. So the principle is the same. But when we want to do it or we want to make it real time, we need to go to RSCAD, which is for the RTDS. And that is two different tools, right? In here, we are running the EMT with virtual hill. And then later on, if you want to make it real-time simulator, you just connect the device and that's it. So as simple as that. And we are using the same tool chain, as I told you. So Schematic Editor, Hill SCADA, Typhoon Test, IDE, we can use this functionality. I mean, it's the same experience, right? It's the same experience as with the Hill real-time device. So we're not connected to the real device, but we can experience as if we are connected to the real-time device. So the student or the user can start developing the model and then trying to simulate and see and verify if it is good enough or not, because it can be used to design the hardware, like the power electronics, the bridge, the converter bridge, or it can be used to design the control itself, right? So we need to have it, like, I mean, this process over and over again, right? I mean, we need to refine the design and see how it works, and then we don't want to, because also the Hill device is quite expensive for us. So, and we only have one in here, so we cannot give all the students with the Hill, but we ask them to use a virtual Hill device to ensure and be prepared, right? Be prepared that if they need to run using a real-time device, the Hill 604 that we have right now, they're already gaining the experience of using the software, and also the model can, I mean, can be ensured that it works properly. So that is the process using the virtual hill device. Yeah, and as I told you before, the same model is used for real-time simulation. So it doesn't really need to change anything, just connect in the device manager over here, connect the hill real-time device. Otherwise, it will always use the virtual hill device. And it is perfect for flipped classroom because student can start modeling, right? Can start modeling, develop the model, try to have a simulation and testing some theory. That's what we have developed in the module. So, and the best part is you can download it for free. Right? I mean, yes, we have we have Hill 604. We purchased that one, but if you want to use, you don't really need to have the Hill 604. You can just download it. Some of the modules might not be available. So because we are purchasing the Hill 604, so we have the access to all of the modules. For example, if you know the MMC converter, there is an average model for that, and that average model is only available if you are purchasing the Hill devices. Otherwise, you need to develop your own model for that. But power system functionalities are there, so you can start testing if you want to. And control, yeah, you can develop the control, the machines over there. So yeah, it's perfect for flipped classroom, and it's also free, right? So you can download it, use it, and yeah, you might need to register to the website in order to download it, right? But yeah, I mean, I can show you later on. And the user interface is like this one. I guess Marcus has shown to you. So we have two different windows. This is a different concept as if we compare with another software like the PSCAD, for example, or Power Factory, where they only have one window. But here we have two windows at least. One is this one. This is for the schematic editor when we edit the electrical part or the control part. It's developed in here. And then in the right hand side over here is the SCADA, which is the user interface when we want to show some results. Also, if you want to interact with the model, then we do it in here. So this looks like the real lab, right? I mean, because you connect the cable and put it in the background, and then you have another panel. Yeah, this one is the panel, right? So the one that looks good is in the panel. So the connection is behind, so usually like that. And also it looks like lab because when we have something wrong with the connection in here, or the output is not as what we think or what we want, then we need to stop the simulation and do some changes in the schematic editor, compile it again, and then run the simulation again. So that is the real life. Like, I mean, as compared to PSCAD or Power Factory, you can interact with the schematic directly, but not in here. So you need to be careful, and we also can teach the student that if you want to measure something, then use probe, right? As in real life. So this is a good experience, and I hope Typhoon doesn't change this feature because this is good for student. So yeah. So this is the two windows that mostly use. And now how I use it in a classroom, or how will I use that for the lab work? We have prepared something, and the things that we would like to show the student that we teach the theory to the student, and we teach the theory to the student, and by using the simulation, we want them to understand better, right? So and by using the Typhoon, it helps us to do that. So for example, if we have this guy over here, so wind and PV system, the one that we spoke about in the previous presentation as well, like microgrid should have a wind, should have a solar panel, the similarity between the two, they are a complex system, right? They are a complex system. So this part, there is a solar panel. They have this characteristic, right? And we can model the PV characteristic in Typhoon. So yeah, and in wind we have a generator, same as generator, same conventional generator. You can have AC generator, DC generator, whatever you like over here. And then we have also the power electronics part, and this is not only consists of the electrical part, but it's also the controller part, like the MPPT, right? And then the inverter also needs some controller over there. So and then also the grid, because we need to measure the when we integrate the renewables like wind or solar panel, we need to measure the integration or the interaction between the inverter and the rest of the grid. So actually what we did is that for the student, we separate this complex system into different parts. For example, using the Typhon Hill, we can start learning about the basic electrical engineering, like Thevenin, Norton superposition theorems, and also RLC resonance, because that is important for measuring the harmonic. And it can be done in Typhon Hill. And this is the example of the, yeah, I guess this is a RLC resonance. When we have RLC resonance, yeah, this is the schematic. We develop the theory, and then we show the how to use or how to build this one and how to simulate that. And also the electric machinery. There are models of DC machines, AC machines, including the DVIC, the one that is used mostly in wind turbine, transformer. And what we can do with that is a magnetization characteristic of the DC machine. We can simulate that one, speed control, equivalence circuit, etc. So this is one of the example when we have a separate excitation for the DC machine. We use a different excitation and see how that can influence the behavior of the machine. And actually it's not only one machine, but we can, sorry. Actually, there is also an option to to couple two machines. One act as a generator, and the other one act as a machine. Motor. Sorry, generator and motor. And we can couple the speed, or we can couple as a torque. Yeah, I mean we can do it as if we are in the electric machinery lab, right? But now everything is in a model, right? And this is a transformer. When we have two transformer, like yeah, we are paralleling the transformer to work together and see yeah, how it looks in a system. We measure the voltage, we measure the currents, and also the power factor angle. That is in the machine side. And the control system we can also develop using a Typhoon. And we develop a module to see the step response for the first and second order system, because what we are dealing here is that the student, right? Because so we start with the step response, and yeah, we have the theory of control as well, and we have MATLAB. But right now, since we are using Typhoon, it can be directly connected with the electrical part and also with the motor itself, and see when we are changing the P, the proportional gain or the integrator gain, what will happen. And we also develop the for open and closed loop speed control as well. And the power electronics, there are some bridges, different kind of bridges. that can be used for the rectifier and inverter. And we also develop a module to test the firing pulses for the IGBT. And yeah, this is one of the examples that we when we use a square wave signal to fire up the single phase thyristor rectifier. So when we use different frequency or different angle, then what will happen with the DC voltage in here? Then that's what we are trying to do in here for the power electronics. And then for the grid side or the power system side, we can measure the, because this is an EMT, so all the phases are there. So we can have a explanation or simulation regarding the sequence network when we have different kind of faults, like the three-phase fault, and also single line to ground fault, line to line to ground fault, and yeah, those type of fault will have the impact in the sequence network. And yeah, we can show the student that okay, this is the concept, and when you do the simulation, this is what you get. And yeah, and there are also some standard test system from IEEE, for example, the IEEE 13 bus available. So whenever the student ready with the development of wind, for example, wind model, then they can start, or PV model. We have a problem with the PV rooftop right now, so they can start using the IEEE 13 bus to test their concept, right? This is the example for having the grid fault. We have dynamic grid fault over here. We just measure the line-to-line voltage and how to convert that into a sequence network and see what happens when we have different kind of fault. And yeah, this is the result example from the fault. So yeah, and so the modules that we have developed consist of the theory, what is it behind the explanation behind the things that we'd like to simulate, and then step-by-step instruction in the modules, how to develop the models, and some expected results. So if the student could not get the same result, then yeah, there must be something different or wrong in their modeling approach. And yeah, this is just an example, and it's in Indonesian language because our target student is in here in a UGM. So yeah, maybe I will try to see if I could connect with the Hill and just show you one of the example for this. Yeah, for example, this is the, oh, where it goes. This is the module that we have developed. So we have, yeah, it's in Indonesian language. So I'll try to translate it to you. So what is the purpose of the module? It is explained in here. So in this case, it is the operation of three-phase thyristor rectifier, and see how the output might differ when we change the firing pulse. And the theory is like this. So we have the schematic for the three-phase thyristor rectifier, and this is the output, and some explanation as well. And then here is the step-by-step on how to do the simulation, right? So you can have this one. And in this case, it's there is an example for that example model that just I mean, giving out the purpose of this one. So, and then some of the expected result that we have done. So if they're not getting the same result, then there must be something wrong with their simulation. And the things that I would like to show you next is yeah. Yeah, I have this one, Typhon Hill Control Center. So as I said to you, or Marcus maybe have also shown it to you, the only difference is here. So we don't have the Hill devices connected. So just download it, and then yeah, you have it. Although you don't have the Hill devices, you can still run simulation and use it for example, the courses. And if you go here, this is a permanent license. So actually it was expired 31st of March 2000 this year, right? But then it will automatically extend. Now it's extended to next year, right? So I still have 346 days left. But don't worry with that. If you are a student, register to their website, download the software, and using the activation key that is for you, then you will get it 1 year. And then if it is expired, then it will automatically extend it. So don't worry with that. So, and then I will just run one of the example. Was the 6, I guess. This one is number 6. Yeah, number 6. And yeah, maybe for the student, it will, I mean, for the startup, it requires a while, especially if you're using the older laptop or older PC, because yeah, it's quite big, the libraries and stuff like that. So during the loading, it takes a while to load the Typhoon. So here you can develop the electrical part, and you can also have the control part. The blue one is the control part. The black one is the power, right? The power path. So we just compile the same procedure. If you are testing it in a real time as well, it's also like that. And then it will pop up something like this. So because I don't have the Hill device, then I will just use the virtual Hill. So I need to click this one. And yeah, it will take a while. Oh yeah, this is it. So no, not this one. Will be number 6. Yeah. So we just need to run it, and it is there. So this is the simulation result. So when you run it in real time, you have the same behavior. And I've seen a paper which actually using the virtual Hill for their plots. So yeah, it's there. So, and whenever we change the firing pulse, you can change to 30 and see what is the impact for that. You can see it like, oh, okay, the thyristor got delayed to turn on. That's why we have this chop behavior in the voltage, right? And the current ripple is also increasing. And if we increase more of the firing angle, like 70, then we got more of that. So by using this kind of tool, virtual Hill tool, it supports the explanation in the class, and that's the thing that we would like to do more in the future. So yeah, I mean, in the previous one, Marcus always said about the Hill devices, and you can connect. Yeah, I mean, that's great. That is great. But the software is also great. So you don't really need to have the Hill devices. You can start using the Typhon Hill, Hill SCADA to do some simulation, write a paper, developing about the new control concept, new control strategy. That's enough, more than enough, right? And it's always good to have Hill devices. Then you can try, or you can try a real system, right? Real control system, for example, and see if that your concept is working or not in the real world. So this is a example on how one of the example of the module. So we developed the three-phase thyristor rectifier and connected to some R and L load. We can do a lot with this one. As you as you saw, we can have it as a basic electrical engineering. We have not this one, but sources like three-phase, single-phase, and we also have a passive components, standard capacitor, resistor, and stuff like that. So you can have a basic electrical engineering and an advanced one like a converter with the different type of converter. It's already there. And yeah, and the one that I will show is this one. Like if we go to the distributed wind power plant here, yeah, I cannot click even because this one is it's not free. Like, I mean, if yeah, component not available due to missing requirement. The microgrid library toolbox, you know, is only for those who want who has the Hill devices. Since I'm not using that license, the license that UGM has, this is just the free license, then you cannot access this one. But this is more advanced. Like, I mean, you have an average model. You can also develop your average model by yourself. So it doesn't really matter. But yeah, this is just the limitation for the freeware. Okay, this is an example of having a virtual hill. We'll try to continue with the presentation. And this is the last part of my presentation. So after the student gaining their understanding for the basic, then it is the time for them to simulate, right? To simulate with the rail system. And this is an example of our capstone project. So we developed the IoT for microgrid. So the purpose is to develop the IoT infrastructure for microgrid and having a control hardware in the loop testing. And yeah, we have this one is ESP32. This is a microcontroller and it's connected to Typhoon. Yeah. So the problem is like we have a transmission line, we have a distribution line, and it goes to the customer. And now customer are trying to install PV and getting more and more customers in Indonesia as well. They try to install PV. And we have seen a problem that when during this condition, over generation or maybe low demand, there might happen that there will be a reverse power direction, right? So and we don't want that one. And the thing is that it also not only for the reverse power, but also for the technical minimum load that you need to operate at a certain level of the power being consumed by the grid, by the customer. So if it is below that one, then yeah, it might go on into the blackout because it's not stable. So we've seen this problem in Australia, that the what is called the yeah, maybe the transmission operator, they can have the authority to turn off the PV when it is in a low demand condition or in an over generation. And we think that transmission has a SCADA system. They're using their own what is called, I see the protocols. They are using the protocols, and usually not so many parts of the system are involved in the SCADA. And what we're seeing in here is that there are more and more PV are coming. So there might be a lot of PV. So why can't we just use a local controller and make some kind of like microgrid controller? And we are using the ESP because that is a cheap solution for that. Oh, sorry. ESP32, it's microgrid, microcontroller, which is quite cheap. And they also have a Wi-Fi. And then we have a microgrid controller. So maybe this guy can control several numbers of PV in the area. And we are using Node-RED in order to have an interface with another one. I mean, with another SCADA, for example, or user interface with operator. So we built the schematic in a Typhoon, and it looks like this one. Here we have the PV model, like we have the solar panel over here, which has an input of irradiation. Yeah, I guess in the irradiation that make different output of the PV power. And then we have also the converter controller as well. And here we connect with the ESP32, which is not part of the Typhoon, right? This one has been developed in Typhoon, but we have input and output. Sorry, this one is an input. Yeah, this one is input, and this input are connected with the ESP32, and it looks like this one. So this is the ESP32. We connect with some kind of lights to see if it is working or not. And then it's also connected with the Typhoon. So with the Typhoon input output, we can access that one and connect with the ESP32. And this is the Node-RED. So why we need to have Node-RED? Because we want to have the user interface. So now we can turn on and turn off the PV from remote, right? So we don't need to have in the site. It is connected to the internet, and yeah, I can control with that. So, and later on we would like to develop a microgrid controller within the microcontroller unit as well. So this is an advanced implementation of that. So yeah, and it is going to the real-time simulation. So the student has developed the system first in a virtual mode using Virtual HIL, and then when I check the student and see if what they did is correct or they need some changes in the model, then if it is okay, then yeah, they can implement it or they can download it to the HIL devices that we have and connect everything like this one. So yeah, because yeah, this is expensive stuff, so not everyone should not have access to that. So it's only we need to follow a certain procedure before we can use the real devices. So yeah, having the virtual HIL is really helpful in developing this test. So yeah, so the conclusion is that VHIL helps the development of class or lab modules because yeah, students can download it, student can start using it, and then this is the best part. VHIL is free, so it can be installed for all students. We don't really need to have a specific PC to run VHIL, right? Yeah, although yes, I mean for the older PC, then it might take a while to load the control center, HIL control center, but it is I mean you can use it. You can install in your computer. Unlike the other real-time simulator that they need the specific PC for doing the as a host PC. Right? For this one, no, you can use any of the computer. Even it's not only Windows, but they also have the Linux for Linux operating system. So quite good. So yeah, thank you very much for your time, and that's all that I have for today. Thank you. Back to you, Dr. Sajia.
Yeah, thank you very much, Dr. Roni, for very basic presentation. And you can see that Hill and Typhoon Hill very powerful for supporting our teaching and work activities, because now under the pandemic situation, I think this is one of our choice for giving the experience to our student with this kind of equipment. It also can be used for the research and capstone design project in our department. This, I think, very interesting. And please, if there are any questions for this presentation, Mr. Prof, please, if you have any question.
I want to ask.
Oh, I'm not time. Okay, please, Sudhiro, if you have any question.
I want to ask about your. Thank you for the opportunity. I want to ask about your diagram displaying wind turbine and PV connected to a grid directly. We know that both of wind and sunlight have a variable value, not constant value, and it is they are uncontrollable. So how to synchronize the output of wind turbine and PV, so can synchronize with a grid voltage and frequency constant? That's my question. Thank you.
Yeah, thank you, Mr. Sudhiro, for the question. Yeah, in maybe not in this module because we don't have that, but we have a AC system, AC machine that is connected directly to the grid, and have a speed control for the AC machine, and we can show you how that works. And then we also I have also developed one simulation regarding the grid synchronization. So what happens if you don't synchronize with the grid and you connect two sources, unsynchronized two sources, and what is the impact of that, and then how to synchronize. You need to see the phase angle and stuff like that, right? And the magnitude of the voltage and stuff like that. So with Typhon, I can show you that one, but not in here. It's in another computer. But yeah, we can develop a test system for that, for sure. And for PV, it's mainly connected with the grid using an inverter. So, and in the inverter, it always has this PLL. So yeah, you can develop your own PLL, or you can use the one that is provided by Typhoon as well, as an example. So yeah, the way the simulation works is that you need to. That's why we have the theory before you do the simulation, step-by-step simulation. So you need to understand on. I mean, simulation can fail as well. Like if you don't do the proper connection, for example. So that is the beauty of simulation, because it doesn't hurt anything, right? Because it's a simulation, just crash and that's it. But then you will start to develop your, or gaining your understanding after that, and and see if that's the problem and problem solving. So yeah, that will be my answer, and I try to keep it in the topic. And yeah, we can discuss more if you want to have a simulation on that. Okay, I hope that answers your question.
Okay, thank you, sir.
Yeah, thank you very much for answering the question. Any other question? Maybe from Prof. Antonis or other college? Prof. Kumar, here also. Please, Antonis.
I think that this emulator can help in the teaching activities. And if we don't have any other questions, I see that Professor Kumar has connected in order to say hello from the Asian Institute of Technology point of view. I don't know, Professor Kumar, if we don't have any other questions. No, so perhaps she could speak.
I
Yes,
don't have
yes.
any questions, no. Thank you, Dr. Antonius, and thanks, Dr. Sergia, for this excellent workshop. Sorry, I could not join earlier. I could join only.
Sorry, there's a problem with my speaker. But okay, any comment from? Okay, Prof. Kumar, you have any question?
No, I don't have any questions. I'm happy to see the good participation. That's quite nice. And unfortunately, like our students have all exams, so it's a bit tricky time. So that's why not many of them probably joined. Maybe they joined earlier. And my best wishes to your new procurement through the MESfIA project. And I hope it will be quite useful to all your students. Yeah. Thanks a lot, Dr. Sergia. Thank you.
Okay, thank you, Prof. Kumar. Okay, if there are no questions more, I think we can end of this session because it's already maybe over also from the time on the allocation of the time. But before we close this session, maybe if there are any maybe closing remark from Antonis, please,
Yes.
Antonis.
Yes, I have something to share. Well, you can see my screen. Well, if we put to the question, if we meet the objectives of the project, I'm very confident that we have met them. To provide high quality postgraduate education with all the activities that have been presented in the month that has passed, this month actually in April, with closing of this sequence of events in Indonesia. We speak about physical islands, we have plenty of them, about isolated areas in the islands as well. And I have made two slides on in order to finalize this workshop. Both universities in Indonesia that participate in the project, ITB and UGM, have upgraded their suggested curricula to adapt to the needs of the MESfIA objectives. Increased flexibility is one of the key characteristics of both suggestions that were presented today. ITB has acquired via MESfIA project an interesting infrastructure on solar power and its cooperation with loads, inverter, and battery storage. It's one of the state-of-the-art, educational material in terms of hardware in order to to see the conditions for the solar power. A similar infrastructure is also in HMU, both in just before the lockdown. Now, our guest participant, Mr. Lim, and I would like to thank him for his participation, presented the capabilities of the hardware in the loop equipment, and especially the Typhoon equipment on the emulation of microgrids, providing in-depth understanding of the phenomena taking place. The capabilities of the various components were presented to the participants, and he gave some examples of universities and how such an infrastructure could help universities with their proposed configuration. And from your side, from UGM, Dr. Irnawan presented suggestions on teaching and laboratory experiments for this equipment acquired with the co-funding from MESfIA in the UGM. Regarding now the challenges ahead, Professor Tumiran talked to us about the problems in Maluku Archipelago and the challenges faced for the transportation of fuel. He gave us a good understanding of how difficult it is to make a spatial planning for energy systems in such remote areas. And the second presentation by Professor Sudarmono highlighted the problems in another sub-region of Indonesia, and it was inspiring enough to hear the problems that may be caused by the small passing clouds into such small power systems in terms of stability. Moreover, he stated that the steps for electrification may include electrification for some hours, increase reliability, and then cost optimization. I think that our motto has also been proven in this workshop. And thank you for your participation. And you will find the presentations in the next coming days in our website. Thank you very much, all of you, for your participation and for your very nice, achievement to have this workshop in this mode. Okay, thank you very much.
Okay, thank you very much, Antonis, for giving the closing remark. And based on this closing, I think we can end this workshop. And before we close this workshop, please maybe we can take picture together for the documentation. If possible, please open the camera so we can have the full picture of all the participants. Mbak Edina, tolong di-capture. Yeah, our staff will capture the picture. So in this. Okay. Already take picture? Yeah. Okay. Thank you very much. I think we have get the full agenda of this workshop today, and thank you very much again for all the participants, all the presenter. Of course, we with very impressive presentation, and we get many lessons learned from the presentation. And thank you also for the European Union and MESfIA coordinator, Prof. Antonis, and all the team. So this workshop can be held with successfully, and see you maybe in the next maybe workshop or other activities. Thank you very much for all of you. See you.
Thank you.
Thank you.
Thank you.
Bye. Take care. Yeah.
Thank you, Umar, Antonis.
Ciao.